time has expired. Senator Rennick.
Thank you, Madam Deputy President. The great Franklin Roosevelt once said, "There's nothing to fear but fear itself." So it's good to speak to this urgency motion. Can I just say, for the record, I don't support any subsidies at all to any type of energy. 20 years ago, we were fed the neoliberal line, and if we privatised the energy market, the market would fix itself. Well, I can assure you the market hasn't fixed itself. Basically been shoveling subsidies into all sorts of energy. I'll just quote, we've heard a lot about the fossil fuel subsidies, which I don't think are all that high at all, but I'll go into the renewable subsidies. There's $10 billion for a CE Clean Energy Finance Corporation, $5 billion for the Snowy Hydro, which purely exists just so you can have a big battery for the solar and wind. There's $3.5 billion for a climate solutions package, $2.5 billion for the Australian Renewable Energy Agency, another $1.5 billion for a grid reliability fund that got pulled and has now been used for gas and things like that. So, long story short, just at a federal level, there's been $20 billion in subsidies for renewable energy. And then we've got the state subsidies, whereby we've got the ridiculous proposition that the Queensland state government, for example, is paying foreign renewable providers for their energy, undermining our own homegrown coal, which is basically free and owned by the Queensland people. Kogan Creek coal mine actually sits on the coal mine, just gets funneled straight up the conveyor belt, and it's all free because it's owned by the Queensland people. That used to generate about $1 to $2 billion in profits for the state government every year, and now last year it lost $1 billion because it keeps getting turned on and off. So, look, there's lots of things I think that we should address. I think we've got 10 energy agencies just at the federal level. So, the whole energy market is completely ruined, and there needs to be a discussion about whether or not we nationalise all the base energy and start again, because it's out of control. But can I say, I just want to jump onto this other point in the point here. There is no climate collapse. There is no climate science. Okay? The field of science that we are dealing with is called thermodynamics, and it's existed for about 200 years. And it was actually, it was actually started by a brilliant young French engineer, or was created, his first theories were created, Nicolas Leo Carnot. And he came up, actually, believe it or not, with the second law of thermodynamics, which was that the entropy of a system always increases. Now, unfortunately, he died at an early age from cholera, so we don't have his papers. But if we move on to the English scientist that took his work up, which of course was Robert Joule and William Thomson, who later became Lord Kelvin and was the first scientist appointed to the British House of Lords. Now, they came up with the first law of thermodynamics, which is that energy is neither created or destroyed, it's just transformed or transferred. Now, these laws matter because heat is basically transferred in three forms. It's either radiation, which is what we're dealing with when we talk about climate science, convection and conduction. Now, I want to talk about conduction first, because conduction is the main form of heat transfer in the atmosphere. And effectively, that rule applies. So the rule that applies to that is the second law of thermodynamics, and I'll explain it to you. If we have a glass of water, half a glass of water at 10 degrees and half a glass of water at 20 degrees, and we pour one into the other, we know if there's no heat loss, it'll average out at 15 degrees Celsius. Now, what I want you to do is to turn those cups upside down or on their side, and effectively that's the way the atmosphere works. So the atmosphere is basically one big pressure gradient driven by temperature differentials. So the greater the temperature differential, the faster the convection will be. So we see convection in many forms. We see it in the wind, and the other major form of convection is what's known as evaporative cooling. And that's where we have a change in temperature from a phase change. So, for example, the heat will hit an ocean, the water will evaporate, and it will go up as water vapour. And then when it gets to a point in the atmosphere where it cools, it gets to its condensation point, it will then basically condense again and fall to the ocean. And that's effectively a cooling point, a cooling process, hence why it's called evaporative cooling. And it doesn't just happen in the ocean. If we go and exercise, for example, you might sweat. That's also known as evaporative cooling, and that is the major form of heat transfer on planet Earth. And what you'll get is you'll get most of that around the equator, where you have these massive convection cells where the heat rises. Now, it has to be said that carbon dioxide does increase radiation in the atmosphere. No one's denying that. But what's very important is to actually understand the degree or the quantify that amount of heat and the direction of the heat and how that process works. So in order to understand that, you need to go back to other laws of physics. So the first one is obviously E equals mc squared, whereby 600 million tonnes of hydrogen are burnt every second and converted into 596 million tonnes of helium and 4 million tonnes of energy. Now, that 4 million tonnes of energy, some of that comes to planet Earth here, and depending on in the form of a photon. Now, depending on where that photon was created in the sun, if it was created in the inside part of the sun, it'll have low energy and come here as an infrared radiation. If it was created at the edge of the sun, it'll come here as ultraviolet radiation. And ultraviolet radiation has a lot of energy, and that's why it causes skin cancer, because it actually knocks the electron, can hit a molecule and actually knock an electron straight out of its orbit, and that will ionise the atom, and that's when it becomes oxidative and starts causing things like cancer and things like that. But what's important to understand with carbon dioxide in terms of radiation is that it has 4 vibrational frequencies. The first frequency is found at 2.8 microns, and that actually refracts incoming infrared radiation. So that's not actually adding to the heat at all in the atmosphere. The second vibrational frequency is at 4.3 microns, and that is that particular frequency has no dipole moment. So that means it's not electromagnetic, and so it neither absorbs or emits. And then we get to the 2 degenerate modes at 14.8 microns. Now, this is where basically carbon dioxide absorbs and emits heat. And one of the big myths we hear in climate science is that carbon dioxide traps heat. That is an oxymoron. Okay? Heat is kinetic energy, the energy of motion. So every person, every molecule on this Earth will basically absorb and radiate heat. If we were to turn the lights off in the chamber now and put an infrared light on you, we'd all be glowing red. Now, what's interesting with the 14.8 micron is that we need to use Wien's law of displacement to determine at what temperature that will radiate. Now, long story short, the formula for that is 2,888 over the frequency of the vibration, which is about 15. So long story short, it'll radiate at 192 degrees Kelvin, which if you convert back into degrees Celsius is negative 80 degrees Celsius. So long story short, carbon dioxide does emit heat at about negative 80 degrees. So you've got to go somewhere up about 10 or 15 kilometres in the atmosphere to actually get carbon dioxide to actually refract heat. So long story short, the amount of heat that will increase as a result of increasing carbon dioxide in the atmosphere is very marginal, because let's not forget that while you might have 430 parts per million of carbon dioxide, it's not the biggest greenhouse gas absorber in the planet. The biggest greenhouse gas absorber in the planet just happens to be this thing we call H2O, which is water or water vapour. Now, that at about 75 degrees humidity and 25 degrees Celsius is about 15,000 parts per million. So if we add, another part per million, the increase in heat is what's described as it increases in a negative logarithmic scale. So if I had 10, for example, patty cakes and I got another cake, it increased by 10%. If I had 100 patty cakes and I had another patty cake, it increased by 1%. So gradually the rate of change, and those of you who understand your calculus will know what I'm talking about, diminishes. So long story short, the whole thing about radiative heat is overblown, because most of the heat transferred throughout the atmosphere is through conduction, and the other part of, and if it isn't through conduction, it'll be through, convection, and if it isn't through convection, it'll be through conduction. And that is where if one molecule, so it'll absorb a photon, heats up, it'll bang into another molecule, and it passes energy to that other molecule. Now, we'll apply the first law of thermodynamics there. So basically, the energy gained by one molecule will be lost by the other molecule. You cannot increase the overall energy in the system. So long story short, there is nothing to worry about at all. We're not going to have a climate collapse anytime soon. The first time you'd expect to see a climate collapse is in about 3 billion years' time, when the sun starts to burn out and it'll start to blow up into a big red blob, and it'll gradually come out and it'll consume Venus and then Mars and then planet Earth. But you haven't got to worry about that, because we'll probably life on Earth will probably come to an end in about 1 billion years' time, when all the hydrogen is slowly evaporated out of the Earth and water will cease to exist. And as you all know, when water ceases to exist, it's kaput for all of us. So thank you very much.
Thank you, Senator